Good afternoon, everyone. I welcome you all to week 8 live problem solving session for the course of analog electronic circuits. Am I audible clearly? Is my voice clear? If someone could respond.
Yes, ma'am.
Okay. So let's quickly begin today. So today we'll be solving problems based on op-amps. So last week and before last week we worked upon differential pair and OTAs. Now we are working on op-amps. So it's like this black box, this triangular box of op-amp consists of those OTA structures inside. Okay, why I'm saying it to be an OTA structure inside? Inside this triangular box, I'm saying that there is like OTA circuit inside this triangular black box that we can see. So my question is, why am I saying that this this op-amp consists of an OTA, not a differential pair? Yes?
So in a differential pair, we may have two outputs and we'll get the
Yes.
difference of two outputs, but in a not.
But here, since we have single output op-amp, so this basically shows that this op-amp consists of OTA circuits. Alright, so quickly starting with today's session. So this is the first question that we'll be solving. In this particular question, we can see there is this circuit consisting of R's and C's, where all the components have their corresponding values, and we have to find out the location of pole in this particular question, and corresponding there is another question, the next question, which says like you have to find out the zero for the transfer function. So first of all, what will be the transfer function for the circuit?
It will be
So first,
Z2 upon Z1,
yeah, so first
where
thing
Z2 is
that we need to consider is what is the configuration, right? So what is the
inverting
configuration?
op-amp.
It is an inverting op-amp. And when we say inverting, we know that A equal to, or to be specific, H of S equal to minus Z2 by Z1, where Z2 is this and Z1 is this. So this is Z2 and this is Z1. So simply we'll substitute these values, and finally we'll get Hs to be how much? What will be the expression for the Hs? So Z2 is R2 parallel C2, right? And Z1 is R1 parallel C1. So it will be So this is finally the transfer function that we'll get, right?
Yes, ma'am.
Correct, no? So here what is asked, like we have to find out the poles and zeros of the transfer function. So what is the value for pole?
minus 1 upon R2C2.
Yes, minus 1 upon R2C2, whereas 0 will be minus 1 upon Rn7, right? So since these values have already been given, so we have to substitute the values of R and C, and we have to report the values for pole and 0. So can you simply substitute these values and let me know what is the exact value, numerical value for the pole and 0? So you can see like R1, R2 are 4.1 and 1.3 kilo ohms, C1, C2 are 7.4 and 8.3 picofarads. And since you have to report in radians or megaradians per second as it's mentioned, so you need not to go for 2 pi, right? So can you quickly calculate and let me know?
Ma'am, pole is minus 92.68
Right,
megaradian per second.
right. And 0?
32.9.
Yes, 32.96. Correct. So this was a very simple problem, right? There's nothing to do. Now moving ahead. So in this question, here also you can see an op-amp. Its output is connected to gate of an NMOS. Okay, and this is a load resistance. So in this question, K has been given, lambda has been given. So your K is 86 millisiemens per volt. Lambda is zero point 0.1 volt inverse. Gain of op-amp is also given. A, let's say it is 554. RL is given 43 ohms and VN is 1.2 volts. Okay, so you have to find out what is the output impedance looking into the source of the MOS device. So which terminal is source? So this is gate. What is this particular terminal of the MOSFET?
Drain.
Yes, so this is drain. So this one is source. So what you have to find out is the output impedance looking from this particular terminal. That means Z out at this particular point. Clear? And this circuit is known as voltage regulator circuit. Okay. So we have to find out this Z out. Tick. So for that, what we'll do, what are the things that are known to us? We'll proceed step by step. Okay. So since these things are known, and we can see that there is one single path for current I. This current flows through the MOSFET and this will flow through this RL. So will there be any current in this particular direction? So will
0
the
ampere.
0 ampere, right? So here it will be 0. Why? Because the
No, ma'am.
current entering to the current entering to op-amp into the op-amp is 0. So we only have one single current path, so single current will flow through this MOS device as well as this resistor, right? And since this is an op-amp and gain is comparatively like okay, gain is high only, right? So for this particular gain, we can write this Vn to be equal to this uh, terminals voltage through virtual short concept that we know, right? So through virtual short concept we can say like these two voltages are equal. So if these two voltages are equal, then I will be simply Vn by RL. Can we write this? Is this okay? Is this clear? Can I
Yes, ma'am.
write this I to be this Vn by Rn? Right? We can write it, no? So if we calculate this, it turns out to be 27.9 milliamperes. Okay, and this is also equal to ID, that is the drain current from the MOSFET. Okay, now since we know ID, so can we find out GM? What is the expression for GM in MOSFET? So you already know K and you already know ID, so you can write 2 root under KID as your GM. So this is 2 root under 86 millisiemens per volt into 27.9 milliamperes. How much is this? Can you quickly calculate? What is the value of GM that you are getting? And similarly, GD is equal to lambda ID, right? So R naught is 1 by lambda ID. Lambda is known to us, that is 0.1 into 27.9 milliamps. So you also know the value of R naught. So what are the values for R naught and GM?
Ma'am, GM is 97.96
Yes,
millisiemens.
millisiemens. 97.96 millisiemens. And what about R naught? So it turns out to be 358.4 ohms. Okay. So we have got GM and we have got R naught. Okay. So here we have to find Z out. That means practically how do you find Z out? So what you'll do, you'll apply a small voltage source, okay, V, and you'll see a current drawn from this particular voltage source. So your Z out will simply be equal to V by I. This is clear to us, right? Is this clear to everyone?
Yes, ma'am.
So now what we are saying that let's say we are applying this small voltage V, okay? So if small voltage V has been applied at this particular point, that means that small voltage V will come to this node as well, right? And since this is an op-amp, we know for op-amp V out is actually gain into V plus minus V minus. So it is the it so basically op-amp amplifies the differential input, right? And output will be simply gain times the differential input. This is clear to us. So at this particular point we are saying, so earlier both of them were at Vn, but now there is a small change of delta V. So what is that small delta output that we'll get at the op-amp's output? It will be A into 0 minus small v. So that is V out will be minus AV. Is this clear to us?
Yes, ma'am.
This is clear to us, no? Now, okay. So here at this particular point we have minus AV. This is clear. Now let's take this circuit. Yes. Yeah. So here we got minus AV. But if you see carefully, this is actually VG, right? Small VG, let's say. So the potential at gate we found out that we have found out is minus of A into small v, right? Now we know the universal current equation for a MOSFET. What is the universal current equation for a MOSFET? Or you can say the small signal current equation for a MOSFET. ID equal to GM plus GD right? This is okay to everyone, right? We have seen this equation, we have used it earlier also. So here we'll simply substitute. Now what is the value of VG? It is minus AV. And what is the value of VS?
V
Small v. And
small
what about VDS? What is the value for VD?
V plus V.
VD will be plus V.
No, sorry, ma'am, minus V.
Yeah,
Should be
so
minus.
VDS will be minus V. So it is basically 0 minus V. Because VD may there is no small signal, so VD will be 0, right?
Yeah.
So ID will have minus of V GM A plus 1 minus of V by R naught. GD is 1 by R naught, right? So this is something that we know. Now moving ahead. So Z out, as we earlier discussed, it is V by ID, right? Small v and small I. So this small I will actually be equal to small id because there is one single current path here also. And in question also it's mentioned that you can neglect this RL. That is the reason that we are not considering RL. If you carefully read the question, so here it's mentioned that you can only disregard RL. So we are already disregarding RL and we are not considering RL. So for suppose if there is no RL, then whatever current you are getting from this attached new voltage source will be the current change shown by the MOSFET, right? So we can safely write Z out to be small v by small id, and which turns out to be R naught by GM R naught A plus 1 plus 1. Okay, so now we have to simply substitute the values and see what is the value of output impedance that we are getting. So here R naught is already known, it was 358, yeah, 358.4 ohms by GM is 97.96, 10 to the power minus 3, 358.4 into 554 plus 1 plus 1. So can you quickly solve this expression and let me know what is the value of Z out that you are getting? And if we carefully observe over here, till the time you are solving, I would like to say that the direction of ID is actually opposite of I. Is this clear to us? So the current is coming out of this voltage source, and this will actually enter the source terminal. Whereas when we write this ID, so this is the current coming out of the source terminal. So here you can see there is this extra negation, and if I write Z out, so I can simply write V by I, no? So this negative, the negative, extra negative that we are getting, negative sign, this will be eliminated. This is because of this thing. So you can keep this also in mind. I just ignored it, but yeah, this you can keep in mind. So you'll never go wrong with the signs. Okay. So what is the value? Yes, Subhash.
Yes, ma'am. So I have a question regarding the circuit. So
Okay.
there is a negative feedback, right? Is it actually reducing the gain of the overall circuit? The reason I'm asking this is the op amp has a gain of nearly 554,
Yes.
and it's followed by a common drain amplifier. So common drain has a gain of approximately it's 1. So if we actually don't have the negative feedback, so our overall gain will be approximately around 554, but it's actually reducing our gain of the circuit, because in this case if there is a negative feedback, our output is approximately equal to input, right? So,
Okay, okay. So basically, what you are saying that first of all, first things first. When there is an op amp, it's and there is a negative feedback, it stabilizes the circuit and gain reduces. So is that getting applied over here? And next question is, in our case, our input is equal to output. So is it true or not? Am I getting it right?
yeah.
Okay. So
In our case, input is equal to output. I
yeah,
understand.
yeah,
So we are
because
just
we can see like this configuration is somewhat similar to a buffer configuration, right? Because no current flows through this particular terminal, so current will be 0, and this shows that both the points will be equipotential in nature. So V out will be equal to V in, and this V in comes here. So we are getting a circuit which is almost similar to unity gain feedback. And as so A that was given, which was 554, it was open loop gain.
yeah.
And after this feedback being applied, you can see that we are getting V out equal to V in. That is our gain to be almost equal to 1. So yes, the gain has reduced, right? Because earlier it was 554, but now it is close to 1, or let's say it is 1.
Yeah.
So gain has already reduced. So we can clearly observe the effect of negative feedback here, right?
Sure, ma'am. So we are actually trading off gain for stability of the circuit, right?
No, stability. So gain has been always a concern in case of op-amp for the stability reason only. So the reason is since open loop gain is so high that like practically if you see it's in 10 to the power 4, 10 to the power 5 ranges, so that if you get even inputs in millivolts or few microvolts, then too you'll see your output getting amplified to close to 1 volts, and mostly noise is very minute value, right? So because of this open loop high open loop gain, what you'll see that always your output saturates, so you are unable to consider your circuit because of open loop and that high gain of amplifier, that open loop op amp. So that's why we go for negative feedback so that it stabilizes the circuit. That means your uh, bandwidth of the circuit increases basically. So your circuit can be used for, so earlier the input margin for your circuit was very less, but now because of feedback, what happens? your circuit is stabilized and you can use it for wide range of inputs. And
Okay.
you can also make it immune to the small signals, very small signals, and basically they are noise signals. Noise is very small in magnitude, and when you go for feedback, so it basically makes your circuit immune to that noise. Hope
Okay,
that
Manish.
clears.
Yeah, thanks for explaining.
No, no, it's okay. So yeah, so finally the output that we'll get is 0.0184 ohms. Okay, so it is 18.4 milliohms, right? This is the Z out that we are getting. Okay, so there is another question. So this is the circuit that is given. So can you see the differences between previous circuit and this particular circuit? What are the differences? I'll stick the image. Okay, so these are the two, right? So 1 and 2. What are the differences in 1 and 2?
NMOS is replaced with a PMOS and
Yes, it's a
the input
PMOS.
is in
And
inverting.
here the terminals have been changed. So earlier the input was given to non-inverting terminal. So here the input has been given to inverting terminal. So in this question also you have to do same sort of analysis, and you have to find out what is the output impedance. Okay, so you have to find the output impedance looking up into the drain of the PMOS. So again you have to find Z out. So we have solved this question earlier, no? Just NMOS has been replaced with PMOS and terminals have been interchanged. Now can you people quickly solve this question in similar fashion and let me know what is the value of Z out that you are getting? Only thing you need to consider is that NMOS has been changed to PMOS and the terminals have been interchanged. Can you quickly solve this question? Do you want to look into the analysis that we have done earlier? Will it help you solve the question easily? So this is where we started. All the parameters are same, everything is same. It's just NMOS has been changed to PMOS and your terminals have been interchanged for the op amp. This is the whole analysis. Okay, so first things first. What is this particular terminal over here? This is gate. What is this terminal?
Source.
Yes, this is source and this is drain. You have to keep this in mind. And we also know for PMOS, our universal equation turns out to be Gm VSD plus GD VSD. VSG VSD. this is the universal equation for PMOS, right? Your GMR naught values will remain same. So how will your Z out change? Or will there be a change or not?
I think there won't be a change. There won't be any change.
There won't be any change. There is a minute change.
Ma'am, scroll up.
Okay, do you want me to scroll up? Yeah. Is this sufficient?
Yes, ma'am.
Okay. So this is the whole analysis of the previous question. Just change it in terms of terminals.
Ma'am,
For
I think the plus one would not be there. Uh,
you got it. You got it right. Why plus one won't be there?
I have
And because source
Yeah, because in
source is at
PMOS,
0.
source is at AC ground. So that plus one is the extra value which comes out in case of NMOS, but which won't be there in case of PMOS. You got it right. So the expression that you'll get for Z out in case of PMOS and interchange terminals will basically be R naught upon 1 plus GM R naught A. Okay, and this value is very close, like it's so again 18.42 milliohms. But when you look into the expression, that plus 1 which was there earlier, it won't be here in this case. That is because source and drain have been interchanged. Easy, no? All of you got this? Anybody has any doubts, any concerns? Is this clear? What is the change in these two questions? Where are the changes that we can observe? Am I audible? Are you people there with me?
Clear, ma'am.
Clear now? Okay. So hoping that this is clear to everyone. If it's not clear, please feel free to ask. So moving ahead with next question. So in this question, it says that this is a sine wave oscillator. Okay, so this circuit generates a sine wave. Here total capacitance has been given to be 24 picofarads. You have to find the value of R such that your frequency of oscillation is 1 megahertz. Okay, so when there is this type of RC network, what is the frequency of oscillation or natural frequency that we know? So omega naught is given by 1 upon RC, right? And F naught will be given by 1 upon 2 pi RC. So here, since there are two capacitances, so each capacitance will be of 12 picofarad. And F you already know, F naught, so you simply have to find out R, which will be 2 pi F naught C. So what is the value of R that you are getting? Yes, what is the value of R?
Around 13 kilo ohms.
Yes, 13.26
So
kilos.
6.
Yes, this is the value that you are getting for an oscillation or oscillating frequency of 1 megahertz. Now coming to next question, this is another type of question. Have you people seen this type of circuit? Have you ever seen this type of circuit before?
I think this is an instrumentation amplifier.
Yeah, this is first stage of instrumentation amplifier. So there are two stages, right, in an instrumentation amplifier. So one is this stage, and the next stage is basically the difference amplifier. So this is the first stage of the instrumentation amplifier. So in this particular stage, so what we have to do, RA and RB have already been given. So it's 18 kilo ohms and it's 225K. It's also 225K. So now you have to find the CMRR. So what is the CMRR? That is common mode rejection ratio. And common mode rejection ratio means, CMRR means it is the ratio of differential gain to that of common mode gain. What do you mean by differential gain and what do you mean by common mode gain? What do we understand by the term differential gain and common mode gain?
Ma'am, when we apply differential input, in that case, what will the gain
What is
will
the
be?
gain? Yes, that is differential gain. And when we apply
And with
same inputs, common
same
input,
input, yes.
and then when we see the gain, then what is the gain? That is common mode gain.
Common
Okay.
mode.
So now for this particular circuit, the idea is you have to find out what is your AD and what is your ACM. Then you'll simply divide the two and calculate the results. Okay. So let's quickly solve this circuit. So firstly, let's go for differential gain, okay, AD. So for differential gain, see these, whenever there is no mention of op-amp gain or anything like that, and if it's not mentioned that op-amp has certain gain, op-amp is non-ideal, till that point we consider op-amp to be ideal with very high gain, so that we can simply apply the virtual ground concept, virtual short concept. Okay, it's virtual short actually. So virtual short concept, the moment there is nothing specific mentioned about the op-amp, we can consider the op-amp to be ideal and we can always apply the virtual short concept. Okay, so moving ahead with that same concept, now we are calculating AD. Okay, so we are moving forward to calculate AD. So I'm letting the inputs be Vin plus and Vin minus, and my output to be V out plus and V out minus, and my gain will be V out plus minus V out minus by V in plus minus V in minus for AD. Is this clear to everyone? How we got this?
Yes, ma'am.
This is simply clear, no? So now moving ahead, so using virtual short, what we'll get, it will be Vn plus and this point will be Vn minus. Let me it's convenient to keep it here. Okay.
Ma'am, as the circuit is symmetric, we can look into only half part.
That also we can do. That also we can do. And
Similar like differential amplifier.
yeah. And here, since this analysis is not that huge, so we can simply go ahead and solve the complete circuit also. You can go ahead with half circuit analysis also. So here I'll show you the complete circuit analysis because that is also very easy. Trust me, it's very easy. Okay. So see, first thing that we need to understand, so if let's say a current starts flowing from this particular terminal, so this current will follow this path and come to V out minus. Is this clear to everyone? We'll only have single current and we'll only have a single current path. Is this clear to everyone? Any doubts in that? So will there be any current in this direction and in this direction?
No.
No, right? This will be 0, this will also be 0 because the current to an op-amp, the input current to an op-amp is always 0. So we'll take that advantage as well. Now simply I'm going to write KCL. So Vn plus minus Vn minus by Ra plus. So here I'm going for complete circuit analysis, like full circuit analysis. You can simply go for half circuit analysis as well. Okay. So V out plus by Rb is 0. Vn minus minus Vn plus by Ra plus Vn minus minus V out minus by Rb is 0. And this current is equal to this current, and this is actually a single current, right? So these are the currents, and all these currents are only single currents, so we can simply equate these two. So Vn plus minus Vn minus by Ra Vn minus minus Vn plus by Ra plus Vn minus minus V out minus by Rb. Now taking like terms aside and unlike terms aside, so let's take V in terms towards one side and V out ones to other side. So it will be Vn plus minus Vn minus 2 by Ra, and if this Vn minus comes this side, so this will be 1 by Rb is equal to V out plus minus V out minus by Rb, right? So Vn plus minus Vn minus 2Rb plus Rb by Ra is V out plus minus V out minus 15 this to the other side. So we'll have this is equal to AD, right? So AD is simply equal to is this clear? So we simply solved the KCL. Okay, this is clear to everyone, right? Now let's move ahead. To find out ACM. So when we are saying ACM, at that time what will happen? If this is Vn plus, this one will also be Vn plus, right? We'll apply same inputs. That's why it's common mode, right? So the moment both are Vn plus, that means here it will be Vn plus and here this also will be Vn plus. That means there is no current flow in this path, so it is disconnected. It means this is equal to this. So this particular circuit converts into this particular circuit where this RA becomes open circuit. Okay, so these two op amps become independent of each other. Now if we look into just one of these op-amps, let's say consider this first circuit, so what we can simply see that this is a buffer configuration, right? So when this is a buffer configuration, what happens? V out will be equal to V in. So gain will be 1, right? Is this clear to everyone? So this is the analysis for ACM. So the analysis for ACM, is this clear to everyone?
I have a question, ma'am. So
Yes.
this buffer has a resistor, right? Does it play any role?
So no, it won't be playing any role. Why?
Okay, there won't be any
Because
current
there
inside
won't
the
be any current, right? So
yeah.
I will be simply equal to 0.
Zero.
So the moment I is 0, this makes these two to be equipotential. So it will be a simple buffer. So this R is also not playing any part.
Sure, ma'am. Understood.
Understand? So is this clear to everyone? How we got our ACM to be 1? Is this clear?
Yes, ma'am.
Okay. So since we got AD as well as ACM, so we'll simply substitute AD and ACM, and we'll get 1 upon 2 RB by RA. So we have to simply substitute the values. It was how much? 225K by 18K. So what is the CMRR that we are getting? Yes, what is the CMRR that you are getting?
28 dB.
28 dB.
28.29.
28.29. And CMRR is always mentioned in dBs only. So we have to keep this in mind. That is a convention that is used. And also gain is always mostly represented in dBs only. So it is the convention that is used. And even in question also it was mentioned that you have to report in decibels. Okay, is this clear? The analysis and everything, is it clear to everyone? Okay.
Yes, ma'am.
So moving ahead, this is another question. So in this particular question, you have R1, R2, R3, 3 resistors, which is 16K, 29K, and 43K. You have to get the expression for Zn or value of Zn. How will you solve it? So what are the things that are evident from this particular question? What is clearly evident from this particular question? So this is output, right? When output connects to input, what we call that?
Buffer.
No, I'm saying when an
Feedback.
output, yeah, so it's a feedback. And in this particular circuit, you can observe that here we have both positive as well as negative feedback. Okay, this is clearly evident, no? We have both positive as well as negative feedbacks. Now, since the resistive values are larger in case of negative feedback, so considering negative feedback to be dominant, what will be the output if you consider the negative feedback to be stronger? So see, if here I want to find the Zn, that means I'll apply a small voltage V and I'll get a current small I, and my Zn will be small v by small I, right? So if this is the small v, that means here also you'll see a small v, and since this is a small v, non-inverting terminal. So inverting terminal will also see a small v. So now
So
here,
1 plus
yeah.
R2 by R3.
So here you will see 1 plus R2 by R3 into small v as your V out, right? So here V out. Now if you closely observe across R1, so the potential difference across R1 is V minus V out, right? So that is V minus 1 plus R2 by R3 into small v, which is minus R2 by R3 into V, right? This is the potential difference across R1. So let's say V R1. This is clear? Acha. What will be the current I? This will be current across I R1. And what about this component? I dash. Will there be a component of I dash?
No,
No.
0 na.
This is 0. So always keep this in mind. Okay? So the moment this happens, we simply know that our small I is equal to IR1. So how will you write IR1? You know VR1. So voltage by resistance will be IR1, right? So your IR1 will be how much? R2 by R1 R3 into small v, right? And your Zn is how much? Small v by small I, right? So this will simply be minus R1 R3 by R2. Got it?
Yes,
Zn.
ma'am.
Now what we have to do, we have to simply substitute the values. R1 was how much? 16, 29, 43. 16 into 29, 16 into 43 by 29 kilo ohms. How much is this?
Minus 23.72 kilo ohms.
Minus 23.72 kilo ohms. So that is the answer. And can you observe something very strange over here?
Negative impedance.
Yes, here you can see that impedance is negative. Generally, you never find impedance is negative, and most of the times, if we say we are getting impedance negative, certain times we say that you are getting the wrong results, like somewhere you have done some sign issues, but here actually in this particular circuit you are getting negative impedance. Okay, so
Ma'am,
this
why
is
is that? Why are we getting negative?
because the connection of this circuit is in such a way, and being negative feedback being dominating, so uh, that is the reason that we are getting this
Ma'am,
type of behavior.
does it have any importance? Means special.
uh, like in general, negative impedance means something different. Okay, here you are getting sign negative, but in general when we say negative impedance, that means mm, so to briefly explain how it looks like, so we always say, so let's say this is V and I, so V by I is always like this, right? So this means, what does this mean? We have positive R, right? Because the slope is
Yes.
positive. But if you get somewhat this type of behavior, so in this case your R is negative. So this is the behavior that is known as negative resistance. Is this clear? So with increasing
Yes.
voltage, your current is actually reducing. And if you carefully observe in this particular circuit, so what is happening is here this particular node. So when you say drop across resistor, so we are saying plus minus VR1, right? So here this negative terminal voltage is higher than positive terminal voltage, like positive sides voltage. That's why you are getting this negative resistance type of behavior. So this shows that the more you increase your input voltage, the current will reduce, or you will get current in opposite direction. That is the basic idea in this particular case. Is this clear?
Yes, ma'am. Okay.
Okay. And in general, if we talk about the representation of physical significance, so it is like when you are increasing the voltage, your current is actually reducing. That is the negative resistance behavior. There are few devices which actually show negative resistance behavior. So you can look into it. There are few electronic devices also that show this negative resistance behavior. Okay, so it's already 4:04. There was another question. It's a different type of question I wanted to touch upon. So, in this question, what is given is an op-amp circuit has been designed for gain of -2. What does this mean? A gain of -2. What does this mean? What is the configuration of your op-amp circuit?
Inverting.
Yes, so configuration is inverting. So that means A, that is minus RF by R, is actually -2. Right? This is clear? And it says that maximum error tolerance in the gain of the circuit is, so error tolerance, error percentage, maximum is 0.04%. So what is the minimum gain of the op-amp that you require? Okay. So this is the gain that we know for an inverting configuration. How your inverting configuration looks like? RF R V out and it is Vx. So A is minus RF by R for this configuration. Another way of writing is, so for a basic op-amp, how do we write its output? It is simply equal to, let's say its open loop gain is A dash. So A dash into differential input. So differential input is how much? 0 minus Vx. Now what is the value of Vx? You will get Vx in terms of Vx as a function of Vin and Vout, right? So you will simply substitute it here, and when you get RF by R, you will simply change it to minus of A, and you'll let this A dash remain as it is. And again, while solving, so you'll solve, first of all you'll substitute this one, okay, and in this also you'll substitute this one, and so this final expression you'll get it like V out by V in equal to function of A dash and A. Okay, so we say this V out by V as A modulation, and this expression will turn out to be somewhat like minus A by 1 plus A by A dash, somewhat like this. you'll get some expression of this format. So basically a mod is a function of a dash and a. Okay, so once you're getting this function of a dash and a, so it is given to you that the maximum a mod minus a by a should be 0.04 by 100, right? This is given to you. So from there, and it is so you have to find the minimum gain, right? So the question is the maximum, what is the gain of the op amp that you require? So what will the value of this minimum gain, and we are talking about a dash over here, open loop gain. So you know this expression. From there, error in the gain ka expression you will find out, and you will get this one. So so this is the flow. So it will take a little longer because you have to do calculations in each and every step, and then you will ultimately get an expression in terms of a dash, that is open loop gain, and a, which is a closed loop gain. And ultimately the minimum value that has been asked, minimum gain that has been asked, it is the minimum open loop gain. So you have to find a dash minimum. Okay, so this is the task. Finally you will get this. Clear? So this is how you have to proceed. It takes a little longer, so you can sit calmly and just solve it step by step, then you will get the answer. Okay, so this is a different type of question. So this time I guess we have touched all types of questions which are present in the assignment. So any doubts in the questions that we solved today? Any concerns? So it's already 4:10 right now. Any doubts, anything that you could not understand? See, whenever there is a op-amp and nothing specific has been mentioned, so we always have to keep few things in mind. Firstly, virtual short concept. If nothing has been mentioned about an op-amp, you will simply apply that virtual short concept. The current going inside an op-amp is 0. Current entering an op-amp, current going to an op-amp through input terminal is 0. Achha, what about this current? I. What about this current I?
Need not be 0.
Yes, this need not be 0. Okay, so because generally people think that current going into an op-amp is always 0, but current going into an op-amp through input terminals is only 0, not through output terminals. So that is also we need to keep in mind. Okay, so if we have to, so let's say if you have 2-3 types of loads attached, RL, some C, CL, and when you are applying a KCL at this particular node, please make sure that you never write this current to be equal to 0. Okay, this is completely wrong. Is this clear? Because this is a mistake which is commonly made by students, so that's why I'm stressing on this point so much. So please never make this current to be 0. This is never 0. There might be a chance that this current is 0, but it's not a thumb rule that this current is always 0. But this current is always 0. This is never non-zero. Clear? So at this point If you don't have any concerns, any queries, we can break at this point and we can meet next week. So thank you. Have a wonderful evening ahead. If you have
Thank you, ma'am.
any doubts, please feel free to ask. Otherwise, we can stop over here.
Thank you, ma'am.
Thank you.